All right, welcome back. I hope you're having an amazing time so far. Our next speaker is Niklas Forsstroem. He is a quantitative analyst at Credit Suisse. Please join me in welcoming him to our virtual stage.
Thank you very much for that introduction. My name is Nick. I'm a quantitative analyst at Credit Suisse, and today I'm going to be talking about leveraging NLP techniques for effective asset classification strategies. So, without further ado, we're going to jump into the slides. So first of all, I want to quickly just discuss why we want to use NLP in finance. So for historical reasons, financial data often comes in the form of natural text. This text is not really produced in such a way that computers can easily handle that text, but rather the consequence is that financial professionals in general spend a lot of time reading that text and basically doing lots of manual work. And one of the big use cases for NLP in finance is that you can sort of automate those processes and therefore cut out a lot of manual work that would otherwise be required. I want to stress that NLP applications in finance are not strictly related to sort of automating those processes, but it's also about creating new analytical insights and increasing accuracy of processes that would otherwise already be sort of performed, because we're cutting out the human factor or the human element when we're doing this. And that kind of brings us to the focus of this talk. So specifically, what I'm going to be talking about is how we can classify assets. In particular, I'm going to be looking at funds in this presentation, but it really extends to a number of asset classes. We're going to classify them according to the exposures that they have. So for the funds, that would be like the underlying constituents of those funds. And that's going to be outlined in the fund description. So we're going to be looking at those fund descriptions and then trying to use NLP models to classify them accordingly. What makes this a bit tricky is that normally in a finance setting, there are stringent criteria placed on the accuracy of such classifications. So you don't want your classifiers to give false positives. That is, we don't want to classify assets that should not be restricted as if they were actually restricted. And I would say that a pretty crude approach that is normally applied in a sort of financial setting is to use keyword-based identifications for these kinds of assets. What you would do is essentially look in something like the fund description in that case for particular words that would indicate that this asset is risky in some way. So let's say, for example, we're looking for funds with an unlisted company exposure. You might look for the word unlisted. For obvious reasons, that's not the best approach, because if you simply look for the word unlisted, a fund description that says this fund is not allowed to invest in unlisted companies would still be picked up by the classification. So it's far from sort of an optimal solution, but it's somewhat widely used, I would still say, because it provides a lot of transparency. So stakeholders can get comfortable with knowing that, this rule-based procedure that we have will produce results accordingly to what we would expect. Now, what I'm going to be talking about today is the NLP-based identification procedures and sort of an alternative to this keyword-based alternative. And that's naturally a more sophisticated approach. The sort of thing to be aware of is that the implementations are going to be more resembling a black box implementation. And so that needs to be kept in mind, of course, when these approaches are implemented. To get things started, I want to look at two case studies just to sort of show you what we're interested in analyzing. So first off, we have a Vanguard 500 index fund. And just looking at the fund description here, we can see that it tracks the S&P 500 index and it invests in large cap stocks. Reading further, we can see that it has exposure towards large US companies. So the meaningful information is sort of summarized at the bottom left. And looking at the time series, we can see that this asset has sort of a lot of, well, it's frequently priced, and there are no immediate sort of warning signs associated with this fund. So if we were to classify this fund, it would not be classified as a risky investment. On the other hand, if we look at this fund, for example, we can see that the investment objective is to achieve long-term capital appreciation through equity and equity-related investments, primarily in a portfolio of small and medium-sized and unlisted Italian companies. So analyzing this, we immediately see that we have unlisted company exposure. which is something that could be an issue when it comes to liquidity, for example. We also have exposure to small companies and sort of a concentration to a small market, namely the Italian market. Moreover, looking at the price time series, we can see that the prices are not very frequently updated. So this could definitely be a cause for concern. And so the conclusion for this one would be that this is something that could potentially be classified as a restricted investment strategy. And so this is what we want the models to pick up. And we're going to be discussing two big models for NLP tasks that are very widely adopted, namely BERT and XLNet. In order to understand those, we first need to go over something called the transformer architecture. And that's what this slide represents. So if we look at the right-hand side, we can see the transformer itself. And this architecture was developed mainly for translation tasks. So that's what they had in mind during the development. It can be adopted for other implementations as well, but for the sake of argument right now, we're going to consider a translation task from, let's say, translating English sentences to French. The English sentence then would be inputted, at the bottom of this architecture into what's called the encoder. So on the left side, you can see the encoder, and on the right side, we have the decoder. What the task of the encoder is to encode this information that we provide the model into an internal vector representation of the different words. So let's say we have a sentence. Each word in that sentence would be transformed into a vector in a particular vector space. That vector space is not arbitrary, but rather the lexical proximity of words in the text would be reflected in that vector space. To understand what that means, let's consider two words that are quite similar to each other. So couch and sofa, for example. Those two words would be translated into the vector space in a similar way so that the vectors are closely sort of resembling each other in terms of where they point, if you think about it geometrically. So that's the main task of the encoder. And the decoder does sort of the opposite. So it takes this representation that you have internally and then transforms it back to a sequence or an output text. In this case, it would be then the French representation of that word. And what you need, apart from just the text when you work with these transformers, is you also need what's called a positional encoding. What that tells you is in which order the words of the sentence sort of flow into the input. That makes a big difference because naturally the ordering of words in a sentence are going to have an impact on what those words essentially represent. So that's additionally something that's provided as an input. As a final remark on this transformer, normally in applications, these transformers are stacked on top of each other. So in the middle, we can see a number of encoders stacked on top of each other, and then also a number of decoders stacked. So that's really what the architecture would look like if you're trying to translate something from English to French, let's say. And for the two big models that we're going to be considering, BERT and XLNet, it's the encoders that are of primary interest. So those are the ones we're going to look closer at. So let's zoom in on the architecture for the encoder. Looking at the encoder on the right-hand side, we can see that it's mainly comprised of two components. First, an attention block, and then secondly, a neural network. We're going to start from the bottom. So we're going to consider the attention block first. And the purpose of this attention block is to help the encoder look at other words in the input as it encodes the specific word that it has in mind right now. So for every word that flows through this attention block, you would consider the entire sentence in which it resides and use that to make a proper encoding. So remember that we're translating this to a vector space. And of course, the words surrounding the word that you're interested in are going to have an effect on how you encode that word. To understand this in a bit more detail, we're going to look at an example. So if we consider the sentence in the middle of the screen at the bottom, it says, the boy thought he was home. And if we consider the word he in this context, if we want to encode that word, we want to essentially get the internal meaning of it. Now, if we only considered the characters that make up the word he, we wouldn't get that much information. But we know from looking at the sentence that he is really closely related to the boy. That's what we mean when we say he in this context. And so this is the information that the attention layer takes into account. So we can see the sort of correlation between the different words indicated by the lines that go between them in the figure. And the more transparent they are, the less of a sort of correlation between those words there is. And so we can see that the correlation between he and then the and boy is quite strong. And so that's where the attention layer really serves to take into account. And so for every word that's fed into the attention layer, the output is going to be a weighted sum of all the words. So not just the word that came in, but really all of them. And the weights of that, or the weights of those words, are going to be sort of defined by how much influence there is in between the words in the input sentence to the particular word that we're considering right now. And remember that these other words are also represented as vectors. So if two words are very similar, that means that the vectors that the attention layer puts out is pretty much the same. So that's how you kind of get that relationship between the different input words and the internal vector representation that they then represent. The next part of this encoder is a neural network on top, which is trained during the training procedure that we're going to go through in a bit more detail in just a second. One thing to note here is that the neural network is applied, so an identical neural network is applied to each and every word that flows through this attention mechanism, or even the encoder as a whole. And the effect that that has is that these computations can be parallelized. And that's quite an important side note, because when it comes to the BERT model and XLNet model, the thing that makes them very good is partially that they're quite big. And in order to train a very big model, you need efficient calculations, or an efficient way of training them. And this, parallel computation enablement is really key to making these models as effective as they are. So, with that said, these encoders really make up what's called the BERT model. So we're going to talk about that model now. And BERT took the world by storm when it came out, because it became state of the art for a number of NLP tasks. It stands for bidirectional encoder representation from transformers, and transformers are, the components that we just discussed. In a nutshell, you could say that BERT is made up by stacking these transformers on top of each other, or more precisely, the encoder part of these transformers. What BERT does is internally it produces a word representation vector with dynamic information about surroundings. So we touched upon that briefly in the previous slide, but we have another example here to the right. So if we consider bank in the following two sentences, firstly, so the man was accused of robbing a bank, and then the man went fishing by the bank of the river. The characters in the word bank are the same. And so if we only used sort of the characters to produce the encoding, that would give us the same encoding for these two words. But with BERT, bank gets a different encoding or embedding. And the reason for that is that it takes context into account. So that's obviously a good thing, because then we have some assurance that the context is adequately sort of taken into account. The way you practically apply BERT is firstly through a pre-training stage. That pre-training stage needs to be on a big data set because this model is really huge. So you need something like Wikipedia or a really big training set where you can get the model to understand the fundamentals of language. So it's not really aimed at the particular task that you're trying to sort of solve with it. That's rather done in the fine-tuning stage, which comes after the pre-training. And during the fine-tuning, that's when you really apply it to the use case you have in mind and create a label data set and so on for that particular application. We're going to go through both of these in more detail in just a while. BERT can be trained for a number of tasks. And for this talk, the two ones of interest are sentence pair classification tasks. So in those tasks, you give BERT two sentences, and then you expect a continuous output value. And one use case where this can be applied is to look at similarity between two sentences, which is going to be applied for this fund classification. The second one that is of interest to us is single sentence classification task. And the difference there is that you only give it one text as an input variable. And based on that text, it would then give a target variable as output. So for example, we give it a fund description and it gives us out if it's restricted or not. We're going to move over now to the actual training of BERT. And so first of all, we have the pre-training stage. As I said before, this is about teaching BERT language and context. So it's not directly applied or related to the end application that you're training BERT for ultimately. but you need to do it on a big training set in order to get BERT to understand the fundamentals of language. This is done with the help of two unsupervised tasks, namely masked language modeling and next sentence prediction. For masked language modeling, what you do is you take a sentence, for example, the quick fox jumped over the lazy dog. And what you do is you replace some of the words in that sentence with masks, and you sort of mask those words from the model. And then you ask the model to predict those words. And you do that for a large set of iterations, and ultimately the model learns to replace those words. And although it's not related to what we're trying to do, it teaches the model to understand in what context you put what word and so forth. The second task is what's called next sentence prediction. And then you give BERT two input sentences rather, and you ask it to predict whether the second sentence follows the first. So as an example, I'm going outside is the first sentence. I will be back after 6. If you have those two, then B would follow A. So the second sentence would follow the first sentence. If you, on the other hand, have I'm going outside, 2 + 2 = 4, they would not really follow each other. So there the answer should be no. And so you go through that training procedure on a very large data set, and ultimately the internal encoders here learn to gain an understanding for language itself. And you should note in the sort of figure to the top left that at the very top where the outputs are, we don't have anything attached yet. So we're just training the sort of core structure of BERT. But if we transition to the fine-tuning stage now instead, you're going to see that we have a classifier attached on top of the BERT model. That is assigned to the C output, which is basically a classifier output of the BERT model. We could go over all the outputs of the model, but that's simply going to take a lot of time, so we'll skip it for the sake of this presentation. But just know that for the applications of classifying things, it's the C output that would be used. And so in the fine-tuning stage, you would then create a labeled data set. In sort of the application that we're considering, if we're trying to classify funds according to if they have a restricted investment strategy or not, we would provide it with input sentences. And then as an output, we would provide whether or not, like the answer to the question, whether or not it's actually should be deemed restricted or not. And so you need to classify this data set. The good thing about the pre-training stage is that the BERT model itself is already sort of attuned to language understanding. And so this fine-tuning data set can be much smaller. And so it's actually feasible to provide a training set for this model and get it to converge within, without creating millions of examples. And so how do we apply this then to the fund classifications that we talked about in the beginning? So I would say there are two, approaches that are quite neat when it comes to this sort of infrastructure and how it can be used. The first one is the obvious one, I would say, where we simply provide an input sentence, like described before, and then we give it an answer to whether or not this fund should be considered restricted. With a labeled training set like that, you could teach the model to classify new inputs like that accurately, and therefore get a much more sort of sophisticated representation of that keyword-based selection that we talked about in the beginning. The even more sophisticated approach that can provide more insights is to train the model on a sentence pair classification task, like we talked about before. What we would do then is we would provide a fund description as input. We would provide a descriptive sentence as another input, for example, unlisted company exposure, to take it back to the example we discussed in the beginning. You could then train the model to predict if those two sentences are syntactically similar. And based on the output that model would provide then, you could classify it in particular dimensions of risk. So for example, one dimension of risk might be exposure to unlisted or private equity companies. Another dimension of risk would be, for example, exposure to countries that you're not perhaps comfortable having an exposure towards. And depending on the risk preferences of the particular investor, you could then tailor sort of the sensitivity to these different dimensions of risk. So in that case, you could provide an even more flexible framework for how to classify these risks that are potentially inherent to funds in particular then. So this is an overview of BERT. Now, since BERT was released, there's also been a model called XLNet, which to a large extent has replaced BERT in sort of performance. So it's, it took over as the state-of-the-art model. And in interest of time, we can't go over all the fundamentals of this model, but we're simply going to talk about the problem this solves in relation to BERT. So in the pre-training of BERT, we discussed basically the masking of input sentences where we predict words that were previously masked. There's a problem with this, which we can see at the top right of this slide. If we have a sentence where we mask two words, for example, when she goes to the, and then we have a mask, she buys some, and then another mask. That could be replaced in a number of ways. One example would be when she goes to the mall, she buys some clothes. Another one might be when she goes to the cinema, she buys some popcorn. Both of those sort of make sense from a syntax point of view or semantics point of view. But we could also get something like when she goes to the cinema, she buys some clothes, which doesn't really make sense. The problem that BERT experiences is because these two words are masked at the same time, we can sort of infer the relationships between the two or the interdependency between the two words that we're trying to predict, which means that the last example there is a fair alternative or a likely alternative from the training procedure in BERT. And that's sort of a shortfall of that model, which is addressed by XLNet. As a consequence of addressing that problem, there are a few other particularities that come in, but we're not going to go through all the details of those now. Just to give sort of a high-level understanding of what XLNet does differently, it takes into account all tokens or predicts all tokens in this sentence, and it does so using something called permutation language modeling. It still sort of preserves a lot of the things that make BERT a really powerful model, but by considering different permutations of these masks, basically switching them around the sentence and predicting sort of each, let's say, constellation of those masks, you avoid the bias that BERT ultimately experiences when it comes to predicting these two masks, as we said before. And so with that, we're going to go over to basically summarizing what we have so far. So the conclusions of this talk are that pre-trained language models, so BERT and XLNet, attain contextual understanding of the fund descriptions that we provide, or any descriptions of assets for that matter. And we can train those to provide accurate asset classifications. By leveraging single sentence classification architecture, we can train a classification model to classify assets as either risky or acceptable according to the training procedure that we discussed. And we can get even more sort of involved or intricate by leveraging the sentence pair classification architecture to build more sophisticated models that categorize multiple dimensions of risk. So that would be, for example, unlisted company exposure and then exposures to certain countries, as we previously discussed. I want to also point out that for optimal performance, it's very important that when these models are trained, you provide it with accurate training data, of course. And so with that, there's normally different filtering procedures that need to be done on the fund descriptions or asset descriptions in general. They can contain a lot of information, and really, we're only interested in the parts that really tell us about the exposures of these funds. So that's definitely something that needs to be considered. Also, a key point to highlight is that these architectures can be combined with the sort of string-based lookup or the keyword identification principle that we mentioned at the beginning. That can be done to make this classification a bit more conservative so that we don't give as many false positives. How we would do that is essentially to require both the NLP classifier to classify this as restricted and sort of a keyword-based classifier to classify it as restricted. Now, the keyword-based classifier could then be made quite sort of generic or in a way that's easy for most funds to pass, and so it would only sort of take out the ones where a false positive is sort of expected, while at the same time, limiting incorrect fund classifications. And so with that, I think there are some very actionable points that I will leave you with there, how these can be applied to fund classifications. And I'm basically going to conclude my call and hand over the stage. So thank you very much.
Wow, thank you. That was awesome. And I know this virtual audience is giving you a huge virtual round of applause. Thank you so much for sharing your insight with us today. For the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and take some time to check out our amazing exhibits. Thanks so much, and we'll see you around.